Alright, so this is physics mechanics, and today we will be learning about measurement. So measurement is extremely important in physics. Obviously, you wouldn't be able to solve anything without measuring things. So let's start with measuring things. So, base quantities, so like length, and then time, and their standards, which are called base standards, are what we use to define all other physical quantities, like speed. So to find speed, we need to know the base quantity of length, and also time, because speed is determined by meters per second. So if we don't know the distance of a meter or the time of a second, we could never figure out the speed of this guy running. So there is an entire international system of units, and they're called SI units. They are base units like kilograms, and SI derived units are like watts. Watt is a unit of power. It's joules per second. We'll talk about that more in later chapters. So there are many ways to make a unit seem bigger and smaller. And these are prefixes for SI units. So like millimeter, centimeter, decimeter, kilometer. Those are all different factors of a meter. So like 10 to the third power is a kilometer. And then 10 to the second power, I don't know if any of you guys know this, but this is a hectometer. And then, so what would be 10 to the negative third power? A millimeter. So how do you know? And so like a kilometer, so like there's 1,000, 10 to the third is equal to 1,000, and there's 1,000 meters in a kilometer. So 10 to the negative third is 1 over 1,000, meaning there's 1,000 millimeters in 1 meter. So let's see how we would find 10 to the third. Well, you could just do 10 times 10 times 10 and just add the 3 zeros. Or you could just do, so once you figure out the pattern, you could just find 10. And then here's 1 0, here's 2, here's 3. And then to find 10 to the negative 3, you would just do 1 over 10 times 1 over 10 times 1 over 10, which is equal to 1 over 1,000. Or do this, and then you would bring the decimal back 3 places. So 1, 2, 3. Wait a second. What you would, so no, you would actually, so if we have 10 to the third, we would bring the decimal place 2 places out. So 1, 2. because we already multiplied by 10, so we can't bring it out for the first time. And same with 10 to the negative 3. You would only do 2 to the left. Wait, what? Oh wait, this is how you do it. So we can write it times 1 times 10 to the third. That equals 10 to the third. So what does 10 to the third equal? Well, we have 1.1 and then you just move it 3. Then you get 1,000. And same with 10 to the negative 3. 10 to the negative 3 is also 1 times 10 to the negative 3. So you can do 1 decimal, 1, 2, 3. And then that's 1/1000th of a meter. Alright. So there's a ton of factors. With the table I have, it goes all the way up to 10 to the 24th and 10 to the negative 24th. So 10 to the 24th is called a iota, and 10 to the negative 24th is a yocto. Alright, so with units, we want to convert factors. So with time, for example, if we have 1 minute, so 1 minute is also equal to 60 seconds. That's an example of a conversion factor. Alright, let's move on to length. So how was the meter created? Well, we emitted light in a vacuum during a time interval of 1/299,792,458 of a second. And when light went through the vacuum during that time, it was exactly, the speed of it was at exactly 299,792,458. Right, let's move on to time. So the Planck time, this is the smallest unit of time. So this is equal to 1 times 10 to the negative 43. And this is the earliest time after the Big Bang which the laws of physics, as we know them, can be applied. Also, 1 second is a time taken by 9,192,631,770 oscillations of light of a specific wavelength emitted by cesium-133 atom. Alright, let's move on to mass. So the international 1 kilogram standard of mass, a platinum iridium cylinder. So it looks like this cylinder. It's 3.9 centimeters in height, which is also 3.911 of a meter. Which we can also say, to find meter, so a meter would be 3.9 times 10 to the negative 2, right? This is the definition of a centimeter. So we would bring this back to So 0.039 meters. Um, and it's also this in diameter. Another mass standard is the carbon-12 atom, which has a mass of 12 atomic mass units. And one atomic mass unit, 1U, is equal to 1.66053.886 times 10 to the negative 27th kilograms. And the reason why there's so many decimals is because this is a very small number, so if we tried to use it on a very large scale, rounding it to like 1.66 would lead to a drastic difference in mass. Alright, let's move on to density. So the symbol for density is P, and P equals mass over volume. And then, so for water, its density is 1 gram per centimeter cubed. The cubed is important, so when you're trying to find volume is always cubed, so you have to multiply base times width, length times width times height. So like for a cube, that all has a one for each dimension, 1 centimeter. You multiply them together, and that equals 1 centimeter cubed. But if this was 2 times 2 times 2 is 8. Alright, so here's a sample problem. So if the ground shakes a lot, the ground can undergo liquefaction. So if you can see this on any video on YouTube. So like if you pump air into sand, it will liquefy, meaning that you could like sink in it, swim in it, you could do whatever you want. Kind of like water. And so the possibility of liquefaction in sandy ground can be predicted in terms of the void ratio. And the void ratio is also known as E, and then E is equal to V voids over V grains. And then V grains is the total volume of sand grains in the sample, and V voids is the total volume between the grains. If E exceeds 0.8, liquefaction can occur during an earthquake. So if V voids is great enough relative to V grains, then so it's over 0.8 relative in the ratio, then you would be able to sink in it, kind of like water. So what we want to know is what is a corresponding sand density P sand. So P sand equals what? And we need to know that solid silicon dioxide, which is the primary component of sand, this has a density of, so PSiO2 has a density, is equal to 2.6 times 10 to the third kilograms per meter cubed. So here's the answer. So we have P sand. So we want to know P sand, right? And we know P sand is equal to mass of sand times volume of sand. So if we figure out these two, then we'll know the answer. Alright, so V total is equal to V grains plus V voids. And then V voids is equal to V total minus V grains. And with this information, we can tell that E is equal to V total minus V grains all over V grains. Because E equals V voids over V grains, so we have V grains, and then V voids is also equal to V total minus V grains. And we figured that out because V total is equal to V grains plus V voids. Alright. So let's multiply the V grains up. So EV grains plus V grains. So we're just changing this, like switching the variables in this equation. We're not adding anything. And this is equal to V total. Alright, so V total is equal to V grains E plus 1. This equation is equal to that. We just shifted everything around. So what we're trying to do is just find V grains, but with this equation. So now we know that V grains is equal to V total over E plus 1. Okay, so the mass of sand is equal to PSIO2 V grains. And why does it equal this? So PSIO2 is the density. So P equals mass over volume. And since the mass is only in the grains of sand, I mean the voids aren't gonna have any mass. So the this would just be V grains, right? So if you multiply this here, you get mass equals that. Okay, now we want the density of the sand. And we got the mass of the sand, which is PSiO2 Oh, well, so we already know it. We also know what V grains is, which is that. So the density of the sand is going to be PSiO2, which is the density of each grain, and then this is over the volume of total. And we multiply that by V grains, which is also V total over E plus 1. We can cross this out. We know that what this is equal, and then we know these variables, numbers. E is 0.8. And then we get 1.4 times 10 cubed kilogram